Hello, everyone. Thanks for having me here to present our work. My name is Fan Yao. I'm an assistant professor at the University of Central Florida. So the title of the talk today is Investigating and Thwarting Hardware-Based Adversaries in Future Computing Systems. Let me first give a brief introduction about myself. So I joined the EC department at UCF in 2018. Before that, I got my PhD degree in computer engineering from George Washington University, and I got my BE degree from Huazhong University of Science and Technology back in China. So I'm leading the computer architecture and system research lab, where we have majorly 3 research directions. We're looking at computer architecture, hardware and system security, cloud and energy efficient computing. So a little bit about research background. As we all know that the security of computing system is a critical concern. I mean, if you look at the current security landscape, we have security breaches that cost billions of dollars globally every year. When we talk about security, there are majorly 2 aspects that we are interested in. The first one is confidentiality, where we talk about we are talking about attackers who aims to exfiltrate secrets from a targeted system. So this could be theft of IP, crypto keys, or bank accounts, etc. And the second primitive or second aspect of security is integrity, where adversaries can try to tamper the functionality of a system or try to damage the critical data in the system to create a system level damage. So in the past few years, the security landscape of computer system has changed quite a lot. The major change is that there has been a huge shift from software level threats to hardware-based threats. I believe most of you probably have heard about the now infamous Spectre meltdown attack from CPU side. So this kind of hardware threats are even more dangerous as compared to traditional software-based threats, as they can compromise both confidentiality and integrity, and also bypass the existing software-based forensic analysis. So it has been shown that hardware is vulnerable in many aspects. In the prior work, we have seen that CPU caches, CPU cores, and memory modules, and all these, a lot of actually hardware components are potentially vulnerable to this kind of attack. So a major research theme of our research is that we only answer the following 2 questions. First, how is the hardware vulnerable in computing system? And the second, how could we build computing system that are robust to hardware threats? So towards this direction, we have 3 research topics that is currently going on. First is microarchitecture security. We'll look at process microarchitecture and see how the microarchitecture design of existing hardware could be a problem in terms of security. And also we have work looking at hardware security of machine learning and security of emerging memory systems. So let me start with the first project that I have been working on for some time. And this one is collaborations with a couple of colleagues from Stevens and George Washington University. So the major, the project is about understanding and taming information leakage in multi-core processors. So the goal is for us to explore side and covert channels due to the multi-core architecture design. So side and covert channel are a form of information leakage attack which typically actually happen between 2 processes. So in general, these 2 processes have different security domains. So ideally, they are not allowed to communicate with each other using any direct communication method offered by the software. However, since these 2 processes all share the same physical hardware resource, so it's possible that we have one malicious process called a spy that try to modulate the accesses of underlying hardware and use this to exfiltrate or steal secrets from a victim process. This is actually very important problem and a critical concern due to the wide deployment of, like, let's say, cloud computing environment where you have multiple tenants sharing the same physical server. So the goal of this project that we are currently working on is basically to look at what are the hardware components in multiple processor that might be vulnerable to this kind of attack. And we aim to study this kind of security threats on real system, on real commercialized processors, and we find the root cause of such information leakage attack, and then we propose mitigation technique that is lightweight, either use lightweight augmentation of microarchitecture, of course requires change of the microarchitecture, or we leverage the existing cost or commercial off-the-shelf hardware support for detection. So the right side actually shows some research result from a recent paper published in Host last year, where we propose use monitoring the cache occupancy of two processes, and we perform advanced signal processing to analyze, to perform a pairwise analysis of these two processes to identify and whether how likely is it that these two processes are under a side channel attack. So the impact of this project, we try to unveil new side channel attack vector in multiple processors and offer understanding about the security impacts of this discovered hardware-based threats. And of course, we want to close this loop, so we also want to provide practical defensive solutions that can secure these computing systems for futuristic attack exploiting these vulnerabilities. So we have a couple of papers that published both from identifying these new side channels, and also we have papers talk about proposing effective no-cost defensive technique. These papers are published in several leading architecture and hardware conferences and journal venues. So we have a couple of papers under submission as well, and we're also working on one proposal under submission, under preparation. So with this, I want to talk about the second project, which basically now we have understanding about what might be the hardware vulnerability in a computer system. One important question that we want to ask is, what is the security implication of this hardware vulnerability to emerging applications? And specifically, we're looking at deep learning systems, because deep learning systems has shown superior performance these days, and it has been applied or integrated increasingly to a lot of critical systems such as image processing, speech recognition, autonomous driving, access control, things like that. So previously, most of existing studies has looking at external threats. Basically, if we have an adversary who is sitting outside of the system and trying to exploit either the input or output of the system to attack or tamper the model of the DN or deep learning systems. Well, we think that that might be a potential threat, looking at the internal adversary that can directly tamper the hardware. So basically, we want to answer the two questions. First, what's the security impact of hardware faults or machine learning, and how to build secure machine learning systems that are robust to internal adversaries. So the right side, we're actually showing a recent paper we published in Resident Security, which I'm actually going to present in 2 weeks. So this work we demonstrate a novel attack. Well, the attack is trying to utilize row hammer exploitation. So row hammer exploitation is a form of hardware attack that where the adversary can just run a piece of code to actually inject fault in the DRAM module. And we assume that if this DRAM module is also used by a deep learning applications, then it could potentially tamper the model of the DNN and create damage to the system. So we actually aim for a very aggressive goal for this attack. Can we inject bit flip into the model parameters of a DNN model so that we can compromise the inference behavior, let's say from a well-trained prediction accuracy to only random guess after the attack is performed. So one example we have shown here on the top is that, let's say originally with ResNet 20, after training the process, we have an inference accuracy of 90%. But after our attack, we can reduce the prediction accuracy from 90% to 10%, which is essentially random guess. And one interesting observation is that our common understanding is that typically deep learning system is quite robust to noise injection. For example, if you have a lot of noise, a certain amount of noise injected to the image, a DNN can still classify this image without any issue. And this is how deep learning system is trained for. But we have seen that DNN is surprisingly vulnerable to internal tampering. Some of the examples we have shown that by only flipping 2 bits in the model weights, we're able to degrade the performance to random guess for the inference phase. So this research actually opens a new direction where we actually motivate the researchers to look at the robustness of machine learning, considering the internal hardware faults or hardware vulnerability. So this is the first attempt to understand the effect of model bit flip on DNN in real system. Actually, we demonstrate this real attack that can compromise DNN using row hammer within just with tens of seconds. And we also plan to provide algorithm level and architecture level solutions to secure DNNs against this kind of force. So we have one publication that's published in Using Security 2020. So Using Security is the flagship conference in system security. It has an acceptance rate of only 30% this year. And we also have one paper under submission to a major ML conference. And we have submitted a proposal to NSF SANSI program last year, actually early this year. And we just got a notification from them like a few weeks ago, this project is recommended for funding. And this is going to be a three-year project collaborated with Arizona State, and UCF is the lead institution. So I'm going to briefly talk about the last project, which is secure by design integration of emerging non-volatile memory in future systems. So in the second project I mentioned about, we are interested in looking at what are the problems of existing hardware vulnerability in two emerging applications. And in this project, we're looking at a different angle. Basically, we know that computer systems is evolving fast, and the researchers are integrating new technology, new hardware to the computer systems all the way. But what might be the security implication of such kind of integration? We are specifically interested in looking at non-volatile memory integration because they promise high scalability and high energy efficiency, and it is projected that non-volatile memory is going to replace DRAM in the near future. But most of the existing studies only look at how do you actually propose optimizations of performance to make it like run faster, more efficient. But most of these optimizations, as we have found, may bring some security issues. And so in this project, basically we're looking at how do we secure this NVM system by design, instead of thinking about remedies for the aftermath of afterthought of some kind of security breaches. So we are trying to explore this non-volatile memory integration in computer systems from device level to how they're integrated in the system and how the software interact with them, and then find potential vulnerabilities. And then we explore ways to improve both the security and the performance together using architecture and system level innovations. So this project with the impact is that we will reveal information leakage vulnerability in system with PCM, which is a very promising NVM technology. And we're going to show the potential attack vectors from different integration points. And then we'll provide secure by design integration of NVM in future systems. So we have submitted a proposal based on this idea at the end of last year. And also we received a recommendation notification for NSF. This has been recommended, and this will be a 3-year project, and it's going to be officially start in October 2020 once it's awarded. So this is a major 3 project I want to talk about. In terms of future research, in the short term, I plan to explore security of heterogeneous computer systems, as we know that these systems with accelerators, with GPUs, they are more performant as compared to CPU-only systems. But so we're planning to explore the privacy and privacy preserving computing platform with GPU and CPU, and also we want to study the temper-aware computing in CPU and GPU. So currently I have this collaboration with Stevens, Texas Tech, Arizona State, with this direction. And in the long term, I plan to explore closed loop secure computer system design and perhaps domain specific computer system as well. So the idea is that we want to actually think about a secure system from top to bottom, from software architecture to hardware layer. So specifically to do this, we will lead secure component technology, we will lead reconfigurable secure architectures, we will lead privacy and temper resistant hardware circuits. So this is going to be the long-term plan, and I will welcome potential collaborations with different experts. So including domain-specific security experts from, let's say, in IoT, smart city, or transportation. Well, I also need help from like program language experts and chip vendors, probably to prototype and build entire system. So with all of this, I will end my talk, and this is the acknowledgement for our funding agency, and thanks my collaborators and students for all this nice work.